Back, everyone. I'm Sandro Rigo from University of Campinas. I'm going to be chairing this first session of Growth 2025, which will be on strategic perspectives for RISC-V. And our first talk is by Yanjun. He's going to talk about how to make RISC-V an international ISA standard. Thank you for coming. The floor is yours.
Thank you. Okay, good morning, everybody. My name is Yanjun from Institute of Software, Chinese Academy of Sciences. So first, I'd like to express my thanks for the USP and UNICAP people here. And it's my first time to come to South American. And I'm very much honored to be speaking in the best university in Brazil and in South America. So my topic today is how to make RISC-V an international ISA standard, fundamental software perspective. So here's the takeaway. First, I would like to give some insights and analysis about our projects and experience during supporting RISC-V software ecosystem. And what is fundamental software? Sorry. First, I'd like to define a scope. Oh, some delays. So fundamental software in this slides, also known as the system software, is a software that directly interact with the hardware. But it's a narrow scope. It's narrow scope of the system software. It's just like operating system kernel, libc, C library, and like GCC, LLVM compilers. So, So why fundamental software matters? Because I think this ecosystem amplifier. I use this slide to show how fundamental software amplify the whole ecosystem. We have about 10,000 semiconductor companies in the world, in the whole world. And while we have so many devices and so many developers, so how these hardware companies can handle all these problems that happen to this hardware? We use fundamental software. So this shows how important the fundamental software is in ecosystem. And since 2019, ISCS, my institute, focuses on compilers, simulators, runtime libraries, and contributing to upstream for RISC-V support. And all these works have been recognized by RVI. We have received RVI Tech Leadership Award, RVI Community Contributor Award, and RVI Community Leadership Award. And this is some examples we contribute to the upstream projects like GCC and LLVM. And you can see there are many RISC-V extensions have been implemented by ISCS. And especially for RV23 profile. And we all know that RV3 profile has been released last year. And now we have focus on the software support of RV23. And this is a QEMU and a Spike. Because I have just 15 minutes, so I quickly pass these slides. This is OpenCV. For example, RISC-V vector extensions have been supported by OpenCV. And my colleague is a maintainer of OpenCV for RISC-V. However, if we revisit RISC-V's mission, aspiration, we can say that there's still a long way to go for RISC-V to become international standard. Why? Here is some explanations. First, let's say the original intention that instruction set architecture has been invented about 1964, when IBM want to make their machines. They have 4 types, and so the software need to be developed for 4 different types. So how to overcome this problem? They invent ISA, instruction set architecture. So the basic idea is one ISA to rule them all. So this ISA has also given the standard interface between the hardware and the software, so they can develop it separately. So, but the current status, there are too many ISAs from the software perspective. The idea is just the software can just deal with one ISA only. But the reality is there are too many ISAs. So the situation become, the idea is the one ISA to run them all, but the reality is we have many ISAs to serve. So let's look into the Linux kernel. When you open up the directories in Linux kernel, like ARC directories, you can see there are 22 ISA support by Linux kernel, and the RISC-V is just one of them. And if we read the codes from the in the Linux kernel, we can see many if devices. Many of these are ARC-related code, ARC-dependent code, especially for x86 and some other like MIPS and other architectures. So from a software engineer perspective, it's hard to, if we have many devices, it's hard to read the code, debug the code, and optimize the code. And also there are too many trade-offs for ARC-related implementations. If we try to understand and read the code, then we can see there are many trade-offs. Here I give some examples. For example, during the call scheduling implementation, memory barrier handling schemes must account for different ISAs. So it's hard to optimize for a specific ISA. And also there's a conflicts between the fast RISC-V and vs slow x86 and ARM. How to understand this? We all know that x86 and ARM architecture is relatively stable, so there's a little chance for that. But for RISC-V, like last year, we have ratified so many ISA extensions. So we need to develop new features for these extensions in software. So, but for x86 ARM, and they prefer the stable versions. So I give example like in Ubuntu 24.0 LTS long-term support version, they use 18. The version 18 for LLVM, then 14 for GCC. But the latest release version is already 20 and 15 respectively. And also OpenEULA. My colleague, Mr. Sheng, will introduce OpenEULA later. And they also choose like 17 and 12 for LLVM and GCC. So it's not. It's obviously it's not the latest release version. So therefore, we have to backport. We have a backport from the latest release version to the mainstream distributions. So as a summary, there are we can see that the fact is, for many fundamental software, RISC-V is far long being treated as an international ESA standard. It's just one ESA, just like other ESAs. So the second part of my slides will show how to build in RISC-V native fundamental software stack. First, I would like to introduce our new plan. It's called RVPU, RISC-V Parallel Universe. So what is a RVPU? In RVPU, we will take RISC-V as a standard ESA, refactor and rebuild the existing fundamental software stack, and to create a new RISC-V-centric ecosystem parallel with the current ones. So there are three steps. First is to make RISC-V as the default ESA for Linux kernel. We start from Linux kernel because Linux kernel by default it's like x86. It supports many ESAs, but actually by default it's used x86 as the major compiling environments. So the second is to replace libc, like specifically glibc, and to change to support RISC-V by default. And the third, we use LLVM to recompile the entire software stack. So the final goal is to boost RISC-V a truly ESA standard. Okay. So this is a comparison about with the comparison with. Sorry, it's a little bit delayed. Yeah, I pressed bar. Yeah, so it's like 3 seconds. 3 seconds play. Yeah. So this comparison about the traditional software stack and the RISC-V-centric software stack. So first, 1, 2, 3. So first, it's we try to make Linux kernel, and actually we choose Linux kernel, and we modify some codes to make RISC-V as a default ESA. And this is the second step. We use a new libc, muscle libc, and many people maybe know muscle C is licensed under MIT license. So, but the muscle C is not as many as APIs compared to glibc, and so we need to. We need to implement some additional APIs for RISC-V. And also, by using this chance, we will modify some old-fashioned APIs for RISC-V. We'll create new versions for the new need. And this has been done by Google about 20 and 5 or 2008, like Bionic C. So this is not a new way. It's just like the same way as Google. So the third step is to use LLVM to recompile the whole software stack. And we know that currently a default compiler is GCC. And some distributions has already used LLVM. And we also had practiced in OpenEULA community. And we have already had LLVM compiled distributions available. So OpenEULA, I will not introduce OpenEULA due to the limited time, and my colleague Sheng will introduce more details. And we also launched a community called Ruyi community. Ruyi is like satisfactory in China. So it's a RISC-V native software stack community. And we committed to jointly build a native RISC-V software stack and driving the evolution of RISC-V ecosystem. And there are already more than 500 organizations has joined the RISC-V community. And this is our agendas for RISC-V for RISC-V community. It's like people maybe see this table, maybe think that it's very much similar with the agenda of RISE. So we have done the same work, but our goal is to make RISC-V as the default ISA. And we have also contributing the modifications to the upstream software community. And we cooperate with some major community additions, OS release communities like Open EULA, Open Killing, and Open Knowledge, Open Cloud OS. So these four communities are all in China, but we have also work with Debian community, and we have a unified RISC-V native distributions and to give it to the industry companies. So this is a RISC-V community that we have some major apps and like browsers, like offices. So maybe it's the second last slide. So I want to say a program that like Dr. Bao had mentioned, the one student, one chip program. We have another program called the Summer Open Source. I think people here, especially students, maybe they know Google's SOC. I don't know if anybody know Google's SOC, Summer Code. Anybody know? Yeah, John, thank you. So this project is just similar as Google GSOC. Google GS has started from 2005. Actually, I am the first bunch of students to participate in Google GSOC and get the certification. So after like 15 years later, I think China should also launch the similar program. So we have this program. But compared to the Google GSOC, we focus on the software ecosystem. So there are more than 1,000 students across 700 universities globally. There are many universities from outside China. So they have a lot of contributions to the communities. So the last slide, our dream is one word, one ISA. Thank you very much.
Thank you very much. We have time for one quick question. Please.
First of all, thank you very much for the overview. May I please ask you to elaborate on the effort necessary to use a microprocessor as a coprocessor or as a hardware accelerator rather than the main processor?
Yeah, actually there's about ISA and micro architecture. Yeah, there's different terms. So in Linux kernel, there are both of them, like ISA support and the microarchitecture support. And we are focusing on the ISA support. And if the specific vendors, they have specific architectures, microarchitectures, they can implement a module, just like device drivers. They can use it to support their own architecture.
Let's take this speak again. Thank you, Jon. So for our second talk, we're going to have a remote talk by Professor João Batista Martins from Federal University of Santa Maria. João, do you hear us?
Hello. Good morning.
Hello, we are hearing you. You can share your slides, please.
Good morning.
Good morning.
Good morning, everyone. Unfortunately, it was not possible to attend this event in person. There was a delay in the transportation between Santa Maria and Porto Alegre, which caused me to miss my flight to São Paulo. Because of this, I am giving my talk remotely. And first, I would like to thank the for inviting me to participate of this important event. Okay, this talk great opportunities in Brazil. New 32-bit RISC-V microcontroller and the residency in microelectronic IC Brazil innovation. Okay, these projects are supported by Minister of Science, Technology, and Innovation. Okay, my curriculum, I am professor in Federal University of Santa Maria. My area is the research in the microelectronics, FPGA, VHDL, low power microcontrollers, designing of radiation tolerant integrated circuits. Objective. This objective.
João,
Oi.
Just a minute, please. We are not seeing your slide. We are seeing your camera. Do you share your slide with the meeting? Você compartilhou os slides? A gente não está
Oh,
vendo.
no. Okay. I'm sorry.
Okay.
Okay.
Now, there you go. Thank you.
Okay. Beginning. My presentation and great opportunities in Brazil. In the two projects in the government, new 32-bit RISC-V microcontrollers and the residence in microelectronic IC Brazil innovation. Okay. And these projects are supported by Minister of Science, Technology, and Innovation of the Brazil. Okay, my curriculum vitae. Objective. The objective of this lecture is to show two great opportunities from Brazil. One concerns the development of a Brazilian microcontroller that using the RISC-V open source architecture. The other is the present the training program in the area of microelectronics, residency microelectronics. Okay. The project is being implemented in the network with 4 other Brazilian universities, UFPR, Federal University Paraná, UNB, Brazilian University, Campina Grande, and the Federal University Minas Gerais. Each university contributes to the project through in the expertise in the complementary areas. Okay, there is also the participation in the private companies that will be users of technology, but they are not limited to them. Okay. SCMD8 is not profile design house that operated together with Federal University of Santa Maria. It does not have a legal constitution. Okay, we have here we have the maps and the locations of the universities of Santa Maria in Brazil. Federal Santa Maria in the state of Rio Grande do Sul, Federal University Paraná in Curitiba City, and the Brasilia in the Federal District, and the Minas Gerais, UFMG, and Campina Grande State Paraíba. And motive this project is my controller. Today, the world lives better transformations. Billion electronic devices will be used by Internet of Things and AI. The pandemic goes global crisis in network semiconductors. Microcontrollers are MEMS electronic devices, 8, 32, and 64 bits. And that date from Uncontrade shows the great difference between import and export in semiconductor in Brazil. Brazil is totally dependent on external production semiconductors. And with SCM through the SMD8 has already produced an 8-bit microcontroller. ZR16 is a microcontroller developed and tired in Santa Maria. It was certified and nationalized by MCTI, in the MCTI Minister and Science, Technology, and Innovation in Brazil. Okay. Main objective this project, the new microcontroller, design a development of a microcontroller 32 bits and the name micro C 32 RFBR with communication RF, Bluetooth Low Energy for use Internet of Things, consumer electronics application. In the technology, in the TRL level 8, technology readiness level or project maturity level in the range the 1 to 9. In the objective is the level 8. Organization of the activity this project. At the top of the project, we have the general coordination. Below, we have the development of the architecture and the activity of the H team, and the digital circuit block and the responsibility of UFSM and the UFCG in the UFSM in backend codification verification, and the verification and the Campina Grande. The analog circuit block is UFSM and UNB. In the power blocks in the UNB, and the converter analog digital, and the oscillator and the FLL responsible the UFSM. The RF blocks is with UFPR, and the software with UFMG. Features microcontroller, 32-bit RISC-V in PULP platform PULPissimo, and the ETH Zurich, and the platform PULPissimo. In the memory SRAM, the 256 blocks, the instruction data, and the peripheral. In the peripherals, in the converter 12 bits, A to C, A to S, CAN, WART, JTAG, SDIO, SPI, Watchdog, RTC, Power, PWM, and the power management unity in the blocks for LDO, in the converter DC, for example, and the free FLLs, and the 2 internal clock reference crystal and the relation oscillator, and the dedicated power supply modules, and the Bluetooth Low Energy, and the using the SIP system in packaging, and the full software stack from compiler to execution environment. Okay. In the core open source RISC-V in PULPissimo, this presentation, in the core RISC-V, in the modulo and the access memory, and the interconnect memory, and the APB, and the banks memories. Okay. Uh, Microarchitecture and microcontroller. This complete chip consists of an ASIC module and commercial RF module. The modules are encapsulated through the chip system package. The manufacturing technology was 22 nanometers TSMC. Project stats. The project was developed in stage and executed in parallel. Stage one is related to the validation of a chip using the commercial processor core. This stage is okay, and its performance was very satisfactory. We achieved a bill communication range of the 200 meter with an antenna internal out to the chip. Stage two is related to the processor software. We developed a compiler and drivers for all peripherals. This was validating on FPGA, very good performance, okay, in FPGA. Stage three is related to the complete ASIC and all digital and analog blocks were synthesized and silicon include memories and are being delivered in July for test. Okay, is the size in 4.3 millimeters square. This is okay. And finish the number of the professors, researchers, and students with developing the project exceeded 60 peoples. In the 30 months of the work, the final version of the chip should be completed in the second half on the in 2026 year in the next year. Okay. Other project very important for Brazil in the capacity, in the training, in the personals, in the residency microelectronics. I see Brazil innovation in the localization. These spots, the professors and the students. Objective is the project's training of professionals in the area of microelectronics design, but in the technical and management areas, which will be carried out through to the formation of a network of federal university in the country, coordinated by Federal University Santa Maria, in the Paraná, Brasília, Campina Grande, and the Ceará. Network importance, increase the project reach and enable training in the South, Midwest, and Northwest regions of Brazil. Creation of 5 training centers for human research in the semiconductor area, instead of the being on the only in the South with the existing agents. In addition, the course will have excellent quality for expertise of the professors in the areas the digital MS and the RF. Course structure: the course is divided into 3 phases with the training of professionals distributed as following the times. Phase 1, 2, 3. Phase 1 in local training. In the approximate in the original project is 9 students. In the 60 months and 72 confirmed. In phase 2, international experience in the 40 students, 6 months. In the 60 days abroad. In phase 3, in company training, 12 students and for 18 months. Thematic areas: the course with 3 thematic areas: digital, analog MS, analog RF. Fazendo curso in the 760 hours consists of theoretical lectures, practical laboratory classes, practical activities, and mentors related entrepreneurship, guest lectures, insights from the semiconductor industry, design reviews, and critics, evaluations, and presentations. Okay. In training and operation, the courses are taught by professors with expertise in the area of the track. In the UFSM, there is free tracks, and UFPR one track, UNB on track, UFCG on track, UFC on track. Specialization course, all students are enrolled in the specialization course in microelectronics in the license at the UFSM, recognized by Minister and the Education in Brazil. To obtain the title of the specialist in microelectronics degree, and the student must complete the training course phase 1 in the right in the TCC. TCC in the work finish course. Minimum period for specialization course, 12 months, maximum period for completion course, 30 months. If the student choose to take only phase 1 and is approved in the course, he or she will receive a training certificate. Okay. Phase 2. Phase 2 is in the international experience. In phase 2, students will work in groups on a more complex project simulating design house. This will be a simulating environment with communication and simulated clients, project management, startup entrepreneurship, and technical chip designing team. In this phase, students will design a more complex and comprehensive integrated circuit that integrates several components and functionalities, where students from different tracks of the digital system, logic MES, and the RF technical and the management profiles will be able to interact and work as a team. First student spend 2 to 4 weeks immersed in groups dynamics work to define phase 2 project. After this period, students go on a 60-day internship abroad with partner companies in university for the project. They return and complete the project to create a new business in product, simulating, and startup. And the phase 3 in company training. The selected student will be formally placed in partner companies of the project. During this 18-month phase, the professionals will work on various projects in the companies and they will return to the sector to speak to the community at a large event composed of professionals from the industry and academic. In the hosted this student in the Campina Grande, in the Ceará, UNB, Santa Maria, digital track, analog track, e UFPR analog RF. Okay? Thank you for attention.
Thank you, João. We have time for one question. Any questions? Please. We have one question, João.
Okay.
So thank you for the nice description of, about the U32BR. I would like to try to understand better about the final SOC you are proposing. I see your radio frequency team is very small. I look to the final layout. You said about Bluetooth or something about that, or about some kind of range or transmission capability. Did you design this integrated with your RISC-V core? And also, as I'm asking a question, what are the contributions from your design over the pulp environment? So there are two questions.
This implementation, this project is the CP, okay? Is the Bluetooth Low Energy, is the module, commercial module, is the integrated, is the ASIC. ASIC is development for team. This contribution is my controller full in the 50 peripherals in the two modules, various modules analog. For example, converter, ADC topologic SAR in the sigma delta. In the FLL is possible to set is the frequency is the finish in the relation between in the frequency and the number bits for example topology SAR is the 12 frequency 280 megahertz, okay, and the sigma delta in the 16 bit in the frequency the 10 megahertz, for example. It's possible to set this frequency using FLL. This is contribution, for example, in the power modules, converter, DC, LDO, okay, but platform is open source pulp.
Thank you, João. Let's thank the speaker again. Thank you, João.
Okay.
Bye-bye.
Bye-bye.
O Fábio falou para eu dar. Na tela errada ainda. Vai ser esse segundo aqui agora. Isso, coloca a tela cheia aqui melhor. Tá. Okay, our next speaker is Sheng, also from the Institute of Software of the China Academy of Science. Thank you.
Hello, everyone. It's an honor to be here, and I'm very glad to share with you our work to develop the open user operating system and the current progress towards RA23. Oh. Thanks. So first is a brief introduction of OpenEuler. So OpenEuler is an RPM-based Linux distribution, it is an alternative to CentOS. And OpenEuler was open sourced in 2019 and mainly deployed on servers. So according to the survey conducted by IDC, excuse me. Sorry. Good. Thanks. According to the survey conducted by IDC, OpenEuler has taken up more than 50% market share of Chinese server OS market share, and ranking the first in China. And according to the operation statistics, OpenEuler has demonstrated to be one of the most prominent and active open source community in China. So we have been developing the RISC-V version of OpenEuler since 2020. In the last 6 years, we have released more than 12 versions and finally got the achievement that RISC-V is now the tier 1 architecture spotted within the community. So, and now we say that the OpenEuler support has natively support RISC-V. So how we define native? That means we abide by the release plan of the community. We use the same unified source code and the same build infrastructure, and we stick to the same QA standard, and then release the ISO, release the image together with other two architecture of OpenEuler. So we have developed OpenEuler 2403 and deployed them on more than 100 SJ2042 chips. That is the most powerful RISC-V chip in the world at the moment. And that means we used OpenEuler to develop OpenEuler, like daily build, daily test, etc. So how we got this achievement? The answer is the infrastructure. So our infrastructure to the RISC-V is made up of 4 parts. The first is the build infrastructure, and then the CI/CD infra, the test infra, and the hardware management infra. So we have actually 2 build infras. One is the public Euler Maker, which is the official build system of OpenEuler, and the OBS. OBS is in-house used and to help us to fix the bugs, and so as to accelerate the development of OpenEuler official versions of RISC-V. And then the CI/CD infra. So we are offering and maintaining CI/CD services for the following open source projects. First is the OpenEuler, and then for the virtualization stack, we offer and maintain CI infra for Rust VMM, Cloud Hypervisor, and Kata containers, as well as for the storage stacks, ESIL and OpenSSL. And the more projects are under discussion with the community. Third is the test infra. So we have built our test infra based on Lava project. And our goal is to establish the CTS standard compatible test system and support automated test. And as a complement to Lava, we also use the community native test framework Magen. So as you can see, the comprehensive test types like smoke test, functional test, performance test are all available here. I would like to also emphasize that all these test cases and test suites are open sourced. So you can get it from this website. So the last is the hardware infra. So as a RISC-V hardware is increasing sharply, so how can we manage so many hardware or RISC-V test dev boards? We have designed a PCB to control all the boards simultaneously and to offer full-stack services like automated test, native compute, as well as remote hardware access. And I would like to say that the controller of this PCB is also RISC-V. That is interesting. And for more information, you can refer to the Chinese summit this year, next month. Next week, okay. Okay. So the third part would be the work towards RV23 and the upstream. So we are working with Linux kernel 6.6. So the most important part to backport is the hardware probe. So we have done it and merged into OpenEuler master branch. And for user space, we have built the software, we have packaged the software with LVM 20 that has been released on March. And we have already built more than 4,600 packages. That is 93% of OpenEuler. And now the QMU image is available. And our plan for RV23 is that we'll release the first non-LTS LTS version of OpenEuler by the end of September, and the first LTS RV23 version at the end of the year. So I think at the end of the year we can the OpenEuler 2003 specs, the third service pack is conform to the RV23 profile. Okay, we have released. At the moment we have also released a ISO or an image for RV23 to test with on FPGAs with Xiangshan IP inside. We have made the very common types of server apps like web server, big data, high performance compute libraries, and as well as compilers and runtimes, and they are running well. So I would like to share two issues we encountered by developing the RV23 standard OpenEuler. First is the imperfect hardware probe support of vendor extensions. This is very interesting. So we have run the sysbench and got the sysbench crashed with SIGIL, which means the illegal instruction. So under debug, we saw that the LuaGIT runtime probes incorrectly and point to the code path of XTHead extension. So we report this to the community, and to work around, we have to restrict to RV64G during the compilation. The second would be the test of performance impact of different vector unit. So vendors concerns about performance difference regarding the length of vector and agnostic default settings. So as we all know, we have met three different kinds of vector implementation: the single 256-bit vector unit and single Aldura 128-bit vector units. So we set the length of vector to 128 and 256, and got almost the same result. So that means that RV automatically process the maximum number of elements that the current VLAN can handle in each loop. Therefore, with proper RV implementation, there is little need for hard-coded configuration during compilation. That is good news. Good, that's enough. So, as we all know, for RV23, the most important two features are the H extension and the vector extension. So in terms of H extension, we care about the RISC-V secure container. So we have planned to build a bottom-up usable and maintainable software stack on RISC-V platforms that would be orchestrated by Kubernetes, secured by Kata container, and speed up by the light hypervisor like Cloud Hypervisor and Dragon Ball, and powered by RISC-V. And at the end, it will be running on RISC-V. So our plan is to build a fully supported virtualization software ecosystem of RISC-V by the end of 2026. So some of the work has already been done in the upstream community, like first the backport of EIA driver and KVM EIA to OpenEuler and RISC-V, as well as Cloud Hypervisor and Kata containers. All the work has been done upstream. So and some of them have already been released by the community. And in terms of the RVV-based optimization, we have chosen the storage stack. So that means that includes the ASL, ESL, SPDK, DPDK, and Central. So our goal is to build a performance-driven RISC-V vector and Bitmanip extension optimized storage software stack. Enable the modern data workloads on RISC-V servers with efficiency and scalability. And we hold the developed strategy of upstream first. So a lot of work have been done out in upstream. So here, I would like to mention again that CI infrastructure is very important. In most of the time, mostly that is a precondition to fulfill. So our future plan. We would like to evaluate the impact of auto-vectorization and fine-tune build configurations to improve the performance of an OS. And also resolve the vector extension-related build failures and conduct performance regressions. At the moment, there are about 20 packages that failed when we compile this vector with this vector. And we will also continue our work with OpenSSL, DPDK, and ESIL. Yeah. And these are all the information above can be found in this website. And for further information, we can also find the readout in this website. Okay, thank you.
Thank you. Again, we have time for one quick question. Anyone? I have one. Can you describe a little bit more in detail the CI infrastructure that you use, that you mentioned is very important for getting upstream?
Infrastructure?
Yeah, you're using GitHub with Actions. What type of pipelines? Oh,
actually, in terms of infrastructure, so the most important is build infrastructure, and they are also public accessible, and the CI/CD infrastructure as well as the test infrastructure are also public available. So we use it and cooperate with the other colleagues from other companies in order to accelerate the development of RISC-V version of OpenEuler. Okay, so we can find it here. Yeah, thank you.
Thank you. Let's thank the speaker again. Okay, our next speaker is Tanya Dadasheva. She's also remote. Tanya, do you hear us? You are on mute. I can't hear you.
Yes, I do hear you. Hello.
Okay, hello. Can you share your slides, please?
Yes, just 1 second. Two.
Okay, we are getting there. It's all right.
So can you see it?
Yeah, are you ready?
Yes. So hello everyone, my name is Tanya Dadasheva, and today I'm here to talk about global view on independent AI infrastructure. And I'm actually going to give you a view from 3 different lenses, just because of my background comes from 3 different industries. So I will give you a view as a founder of a tech silicon company, as a founder of a open ecosystem close to a foundation, and as a venture capital investor. So this is my 3 backgrounds, and this is what I want to talk today about. So what is infrastructure? And when we talk about open infrastructure, what do we even mean? So since this phrase, it actually was said by Jim Zemlin from Linux Foundation, that tech is always global, but infrastructure is always local. And this is the way I look at it as well. And there are many reasons for that. And some of the reasons are listed here. So there are always regulations, and sometimes regulations go as far as limiting companies to a certain country. So that's another term actually coined by Linux Foundation, techno-nationalism, which is basically also about that, about every country having an ability to support technology locally. And it comes from other questions like, can the company actually support the open source project they're using to build the foundation, so the infrastructure? That's why when we talk about open infrastructure, the question is not only getting these building blocks, but supporting them locally and having the whole, let's say, company infrastructure around that to support it. And of course, everybody talks about supply chains dependencies, and it's not only like foundries, it's goes to the software supply chain as well. Like if you look at tooling that everybody uses Synopsys. And that's one of the bottlenecks of the supply chain as well. I mean, we can talk about that in more details, but I think one of the most kind of on the mind of everybody, infrastructure these days is infrastructure for AI. And it makes sense. It's a growing market. Everybody's looking at it. Everybody has their own opinion. But if we talk about infrastructure for AI is not just a chip. It's like this whole number of layers that have to exist and have to be integrated, that have to be compatible and co-evolve together. So this is a few layers that just like I identified, but I'm sure they like can be broken down to quite some extent. I just think that looking at infrastructure for AI these days is also reasonable because it has a lot of opportunities as it's not defined anywhere yet. So if you look at classical infrastructure, there is a lot of legacy. You can try and redefine it as open. But in AI, like it's all emergent anyway. So it's easier to look at it. And it's an opportunity to actually see and seed the market with what's possible. But what do we get on the market? We get on the market partnerships like an Oracle that want to deliver sovereign AI. And that is like building AI factories in lots of countries and lots of different geographies. And this is as far as possible from open infrastructure. Because if you look at it, it's obviously very proprietary. It's obviously based on whatever sex nobody really knows. And like obviously they have a lot of leverage and a lot of money. So it's not like any single company can fight them, but the open ecosystem still can. And again, one more interesting thing about AI is actually that a lot of things already happen in the industry that allow to redefine it. So if you look at this kind of framing and this lens of who can integrate attractive profits in the market. It's really useful when the market and the incumbent value chain has, and it's always like there is an integrated part and the modularized part. So modularized part means a lot of players, but integrated part is that the value is really integrated there. And what happened with AI is that actually already changed. So there was a lot of data unbundling, there was a lot of instruments unbundling, there was a lot of models released with open weights that allowed to unbundle basically training from inference. So there are a lot of interesting things happening. And if you look at how the new value chain looks, it kind of seems like models are available, data is available, compute's available, tools available. You can customize models to quite an extent for yourself. So it looks like this part of the market is now modularized. So the attractive values should just go to the point where anybody can integrate them in different products and basically go and explore different business models and different opportunities. But it kind of only seems this way. And the problem is, this is like, I think what's interesting for this particular conference, because the problem is the chips. And not even just like the chips, but the frameworks and the available software stacks on top of the chips. Because like there are lots of new, obviously, frameworks that appear these days with like different model architectures that they can support. There is obviously Llama CPP and GGML, there is TinyGrad, there is ZML, there are lots of different frameworks appearing that kind of allow you to get away from PyTorch and CUDA. But at the same time, once you start looking at them, there are so many leaking abstractions that they're going all the way to the CUDA kernels anyway. And it's like, I mean, again, Llama CPP is actually trying, but I think it's kind of the only one that's trying to allow you to have an alternative. And it's all very nascent, so there are a lot of opportunities to create something in the alternative. But again, most of the chip companies still do it all in closed source. And even if they don't, it's mostly like one company open source. So I actually really respect Torrent with the open source efforts, but it's one company open source. I actually haven't seen any other chip company collaborate on the same framework, for example. And this kind of codependency, on one hand, it's definitely limiting. On another hand, it's definitely an opportunity, because if there is something that changed in the market, again, creating an opportunity, is inference dominating training. So now, if you look even at how much infrastructure is required for inference, and that basically none of the current frameworks, not PyTorch, kind of suited for that specifically, that definitely creates an opportunity to create a new ecosystem and around a framework for inference specifically. And like, I mean, it's RISC-V, right? So like it's open. What's missing there? Well, it is open as an instruction set. It's not really open if you start looking at the layers of systems that are built on top of it. And that again starts like with what embedded operation system is running there. What's basically people are putting on top of it. Still nobody's really opening, nobody really collaborating on it. And there are different architectures obviously on top, but they all kind of are limited to the kind of host software that people are discussing, and not all the layers in between. And that's why, like my personal opinion, that we need a fully open system and we need collaboration around it. Because otherwise the infrastructure will always have this choke points and these bottlenecks created by large corporations that you will always be kind of serving them by developing stacks on top. And if you look at not just technology, but what's also required for this to exist, well, it's obviously an ecosystem. But it's not just, again, an open source ecosystem in the kind of known way when there are different projects that people collaborate on. But there should be some kind of blueprints that actually combine it all on the system level, because there are not really a foundation that looks at it as a system level today. And it kind of seemed to me that why should we need it? People are really used to building system on top of projects that are available in building blocks. Not really, and I talked to quite a lot of CIOs about this, just like, again, as a company that's trying to do a product. And the problem is that it just, in an ecosystem that changes so fast, it's really hard to commit to anything and to kind of build an end-to-end system, so only hyperscalers can do this. So most even enterprises in Fortune 500 are not really doing this. And I mean, obviously, the other component in this is funding, and the question is, like how the industry should be funded. And my, again, personal opinion, that if you play techno-nationalism game, and if you want to have some local infrastructure, and again, as we said, infrastructure is always local, even if it's open, it's not a VC game anymore. It is a sovereign play. And I mean, there are many instruments, and it's not like we need to reinvent them. There are obviously some instruments that government has to subsidize and to support with grants and whatnot. But the way I look at it, and I think Europe is a really good example with having a lot of grants, but still not really having end products that people like use. And by people, I mean not just consumers, but also companies. And there was a moment at the RISC-V summit in Europe that happened months ago, when people were discussing it on a panel, and they all agreed to this simple statement that to have systems that are used, you actually need demand first. You actually need the demand, and obviously you can't like stimulate consumers to create the demand. They will always just follow. But you can stimulate corporations to form the demand, especially the qualified demand, when they can actually tell you what they need and like what are the specs, what are the at least requirements. Because again, since we're talking about infrastructure, it's not turnaround is not that fast. So it's definitely planned ahead. And then you can have an integrator that takes all the components of the stack and put them together, but also components are obviously open source, so they do need to be synchronized with the global ecosystem, but they do need to be supported locally. There has to be a local integrator, and all of that can use definitely the local institutions and local money, and that could be a whole again, synchronized efforts to do that. Because I don't think if you just give money to certain components of the stack, especially as grants, you will end up with a end product. And I think that's, again, it does help the ecosystem, but it does help the ecosystem in an even way. And in some cases creates even more gaps because, again, even companies that get grants that way, they kind of still use all those proprietary like synopsises, not open tools, and they use the CUDA and they optimize for this and that. So they're not really thinking end to end. And like just to sum it all up, I think it's a really universal problem. So unlike previous discussions about infrastructure, there was a lot of kind of condescending notion that it's for developing countries, and developed countries already figured it out. Not for AI. Everybody at the same level. Everybody's figuring out right now. Regulation and governance are very fragmented. As we discussed, like regulations on a country level are really controversial in some places, and in some places they just don't exist at all. And that is because, especially if there are blueprints and there are synchronization in the ecosystem, then it's actually easier to replicate it in different countries. It's a great opportunity for exports because, again, it's all interoperable. Everybody is agreeing on what it actually is. And it actually can be a great instrument to stimulate the local market development. Because, like, I've seen it, and I've seen it many times, that the governmental funding is used inefficiently. And if you actually have an international organization that agrees on, again, blueprints, not the result, but blueprints, and you can just take them and support them locally, create them locally as an infrastructure, it's actually that develops the country much faster. It creates great opportunities for students to join it, and for young specialists to not go to just other countries with better opportunities. So this is basically what I wanted to talk to you about today. And here is a QR code actually for AI Foundry. It's absolutely non-profit. It's actually not even an organization. It's a community but we try to discuss all of these questions. And one of the main ideas is that it's always a system approach. It's end-to-end approach. So any questions?
Thank you, Tanya. So we have time for one quick question. Anyone? No? Thank you, Tanya. Let's thank the speaker again, please.
Thank you, guys. It's an honor to help.
Thank you very much. And we are going to move to the interview that we have planned. It will be played in a few moments. I just have a quick announcement to make about the lunch. After the interview is finished, we are going to have a small brunch here for those who don't want to leave the building, but we are going to have a break up to 2 o'clock. Okay, so if you have something to do and this time is enough for you to leave and come back, it's no problem, but there is going to be a small brunch here for people who stay with us till there. So Peter, please. Peter is going to introduce the Luca Benini interview.
So on behalf of the GROW organizing committee, I was able to ask some few questions to Luca Benini. He was unavailable to attend the events in Zurich, so that's why he wanted to have the recorded session. So the list of questions that I asked was about the RISC-V, the ecosystem maturity, the performance challenges for HPC and AI world, and in the era of the AI world and HPC, and then standardization and fragmentations, how the RISC-V will be able to be standardized and then avoid the fragmentations or even help the fragmentation in a way to enable for multiple various applications. And the business models, what are the business models that industry has adopted in order to make the RISC-V to be possible and applicable for many business cases as well. So please enjoy the interview.
So, good morning, everyone. It's a pleasure to welcome Professor Luca Benini, a leading expert in computer architecture and embedded system, for today's session. We're grateful for him to attend or making his time available and speak us on despite of his recent busy schedules. So today's discussion will focus on some key challenges and opportunities in RISC-V ecosystems, from software performance gaps and standardization, fragmentation, and business sustainability. So I guess it's all hard questions. No one knows the answer yet, but I'm pretty sure Benini has some crystal balls, might give us the better answer. So these are the important topics of RISC-V continues to evolve and again getting some traction across industries. So Professor Benini, thank you again for joining us. So we are looking forward to hearing your insights. So let's begin. So do you mind if I start with a question, first of all?
Sure.
So the first question was, I think this is the great question that the organizing committee of the GROW assembled. This is amazing. So let me just ask the first question. It's about the ecosystem maturity. So RISC-V has been growing quickly, but its software ecosystem like OS support, compiler tools, libraries, which I'm pretty sure you were involved many of those as well, and still catching up. And somehow, with ARM and x86, in your view, what are the biggest hurdles that RISC-V faces in building more complete and develop-friendly ecosystem? Or at the same time, do you think, is it necessary to catch up, or do you think we need to build something different than the existing ARM and x86?
Yeah, well, I think let's say, if you look at the trajectory, for example, if you take the example of how many years it took for ARM to catch up in the server space with respect to Intel architecture. And it has been a very long process, right? 10 to 15 years catch-up time. Now, the impression I have with RISC-V currently is that this catch-up time has been reduced. significantly. Probably one of the reasons why it is reduced is that the software ecosystem had already a transition from x86 only to ARM x86, and then going from two-pronged approach to a three-pronged approach. It takes actually less time because a lot of the process has been moving along. Now, the other
having the Andrea joining us from Linaro project probably also helps us as well, right?
Yes. The other problem is that you need also strong industry support. It cannot be only academic or volunteering, or even though it is nice, you need to have good, strong industry support. And I think an initiative like RISE that is currently having some of the industry leaders like Qualcomm, Samsung, Intel themselves supporting the RISC-V ecosystem in software is actually helping a lot. So
it's a combination of multiple things coming together, right?
Yes, I'm very optimistic that it is happening. I'm less competent for the mobile ecosystem, but for the, let's say, high performance computing and the server ecosystem, the time we spent to bring state-of-the-art, for example, deployment packages, HPC deployment packages onto RISC-V, was very, very reasonable. Now, so in this case, I'm quite optimistic about this.
Okay, that actually lead into very good segue to the second question, performance challenges. Since you talk about HPC, so RISC-V is known for flexibility. I guess that's one of the biggest attraction that we have. But matching the performance of the established architecture, such as ARM and x86 in data center, especially for HPCs, is quite difficult to do. But in the diversity of now this computing, data center, AI are very challenging, even for existing CPU solution guys, right? Do you think is there any main obstacles for us to close the gap and then somehow take the market lead, or actually leading in the new areas of application?
Yeah. Okay. So I think if you asked me this question maybe a couple of years ago, I would have been less optimistic. And the reason I could have been less optimistic 2 years ago, there are two factors. The first is that fundamentally, a company like Intel was like a big, strong monolith, and with very strong leadership and so on. Now, as you all probably know, there is a different type of Intel, and so a lot of opportunities are opening up because of the weakening of one of the key ecosystem leaders in the high performance space. So that's one factor.
Yeah, I mean, the rise of the NVIDIA and then ARM software from AMD, this is becoming also main driver as well, yes.
Exactly. And the other factor is that this is probably not entirely positive if you view it in a philosophical viewpoint, is that the different international situation with systems decoupling, computing systems starting to be decoupled, sovereignty starting to be a major concern, is actually pushing a lot of continental blocks into developing more aggressively their own sovereign solutions. And RISC-V is really ideally positioned to help these sovereignty efforts, because on one hand, it's a common standard for the ISA. On the other hand, it allows different sovereignty-based solution on a common instruction set architecture.
I mean, no one hates RISC-V, by the way. Everyone loves RISC-V. Yes. So
I think that these two factors combined have, in a sense, changed the picture, and in my view, shortened by a significant amount the time it will take to have a competitive high-performance solution based on RISC-V. Nevertheless, it's still a challenge, because if you ask me what is the single cheap, high-performance chip I can buy based on RISC-V, there is none today. So it's still to be proven.
It's a lot of investment needs to be done to make those high-performance compute architecture available. But I guess the diversity of application, AI coming in, GPU coming in, DPU coming in, probably allows that type of new architecture to evolve as well, right?
Yeah.
Okay, so I guess one of the hardest problem would be this one, in my understanding, the standardization and fragmentations. As you can see, this is the flip of two sides of the coins, right? So open and modular nature of RISC-V is a big advantage, obviously, but then it can be also lead to fragmentations. And given the geopolitical situations and sovereignty of AI, I guess a lot of countries are trying to do their own things, right? So standard becomes an issue or a solution too, right? But how do you see the current challenges around the compliance, verification, execution management affecting the RISC-V adaptation? Because this is not just about architecture anymore or profile anymore. It's about the ecosystem and how do you maintain that ecosystem to make the RISC-V to be more successful, right?
Yes. Okay, frankly speaking, there is, in my view, no good answer to this point. It's a risk.
Right.
It's a risk. On the other hand, let's look at comparatively how incumbent ISAs have evolved with respect to the workloads.
Okay.
So in this case, for example, if you look at what happened with ARM for the extensions toward machine learning,
right?
It took quite a lot of time, frankly speaking, for ARM to come up with extensions that are more and more meaningful for machine learning.
Right.
So in a sense, it's true that having many companies that compete, trying to differentiate on different variations of the instruction set, and not waiting for the standardization process to provide a standardized solution is a risk. Mm-hmm. But on the other hand, the time it took, even for a completely own proprietary ISA, to develop a solution for an application domain is a very long time.
Yes.
So I expect that there is going to be like a Cambrian explosion of variations, people trying to compete and so on, and then the standard will consolidate them. And the time it will take for this consolidation time in the ISA of RISC-V is probably going to be a few years, but it's not that much longer than the time it took an instruction set like ARM to come up with a solution that is good for a specific domain. So right. I agree there is a challenge, but if the standardization process works,
right,
it may lead to a solution that is common, standardized, in a time that is not significantly longer than the one it takes to a consolidated instruction set to find, the willingness to adapt to a new requirements.
Yeah, I think having the open and modular architecture of the RISC-V and allowing the industrial partners and players to lead that direction, and we just become the enabler to put those into standard, is probably a key enabler. Like unlike the previous Intel case of the big guy thinking about architecture and providing that, might not be able to catch up what the industry demand is on the various applications. Yeah. So
the risk, of course, is that a standardization process gets in somehow bogged down into discussions and so on. So this requires a healthy RISC-V foundation, a healthy RISC-V ecosystem. So this is, it's important to have that. But if this works, I don't see why having a standardization process is going to be a disadvantage.
Absolutely. I think we are going in the right direction because at least the RVI, RISC-V International, is part of the Linux Foundation where they have all the structures and organization involvements. I think that from that perspective, we have system support to make this as possible. Whether players will be investing on heavily for making that standardization or not is something we have to see and look for. So the last question would be the business models, right? So many RISC-V companies are still in early stages, and probably there are many people who have succeeded and failed as well. So relying heavily on investor and academic fundings, right? And then what do you think of the path of the sustainable business success look like RISC-V vendors in the future? I mean, Qualcomm is there, Sci-Fi is there. There's many companies trying to do their own things. Do you think you will start to see widespread or commercial adaptation or probability in this space soon?
Okay, yeah, I mean, there are many business models that are being tried out. So it's not for me to say which one will be successful.
Okay.
I think that there will be, for sure, some companies like large companies. You cited the Qualcomm, which is definitely a company that is looking very actively into RISC-V for products. And I also would like to cite some European companies. For example, Infineon has clearly announced the move for their automotive solutions toward RISC-V.
Right.
So I think the road of large corporations, Renesas on the Japan side already has a line of products based on RISC-V for automotive, for communication, and so on. So the large corporations adopting RISC-V lines of products is clearly going to happen. I don't see any doubt around this. Now, the road for startups is, of course, a high-risk road, as for any startups. And I think the idea of the big challenge for many startups is to decide if they want to be a chip company or an IP company. The largest risk I see today is there are many companies that are not decided yet if they want to be a chip company or an IP company. And they have this dual model, which is very dangerous because, if you are an IP company, then you should not make chips and compete with your customers, right? And if you are a chip company, probably you don't want to sell your IP because your IP is your secret sauce for the success of your chips. And currently I see a couple of leaders, at least in the RISC-V ecosystem, that have not decided what they want to do. And this is a risk.
It's a very strange time of semiconductor industry where a lot of OTT company like Google building their own TPU solution for AI. So it's an interesting mixture of what's going to be happening in near future. So speaking of which, do you think the interest and then dominance of this AI application for the computer architecture and so forth will influence or make the usage of that RISC-V better in the future?
Yeah, I mean, I think we need a stronger market with a stronger push and a stronger need for new solutions because clearly a consolidated market that is only growing incrementally is not good for a new architecture to evolve. I think AI is a big push. I think that also, there are some areas of innovation around, smaller market, but highly critical market. For example, space. There is actually very interesting market coming out of space because of the new satellites communication, Earth observation. So these areas are areas that are very good for RISC-V to develop. Automotive seems to be an area where RISC-V is getting a lot of traction. So I think that AI is for sure a good one, because it's one that is really, growing. If this is the only one, I don't think so. I think there are, at least a couple of markets that are, as good as AI in terms of possibility to gaining market quotas. Of course, they are smaller than AI. But, as I mentioned, space seems to be a very good one, or anything related around satellites, and automotive seem to be another one.
Right, because there are a lot of customization can be done, and then a lot of extensions will be able to adopt in there as well. Yes. So just for the final remarks, for the folks who are in São Paulo without your presence, right? I'm pretty sure you had enjoyed your nice vacation with your family. But then for the people there, do you mind leaving final remarks?
Yeah, I mean, I think related to RISC-V, I think we should not, for anybody that is in academia or, starting a company and so on, we should not forget that RISC-V offers you huge opportunity around openness. So in my view, keeping the open nature of RISC-V also in what comes after the computer architecture, after the ISA. So RISC-V open chips, RISC-V based open design automation tools is an extremely interesting areas to be into right now.
I mean,
so
just
I think,
noting that this Grow conference is happening in Brazil, which is relatively a country that we're not really exposed to the semiconductor industry. I think that's the encouraging sign that any country who are interested in architecture or investment in semiconductor can invest and start working together, right?
Absolutely, especially around these open models that allow collaboration across international borders, creating a very good international type of consortia and attracting talent from a global viewpoint, not in a single
education and universities.
Exactly. And, you know, as a professor, I've been so excited about RISC-V because it made, you know, research and education so much easier than before.
You had so many programs in the ETH Zurich, you know, that was so successful. And I'm really great to see that type of success happening around the world as well. So thanks so much for your time today. It was a great pleasure again and making your time available for this great opportunity. Hopefully we can see you sometime in the future in next Grow events or in near future.
And I hope to be there in presence because Brazil is a great place I want to visit.
next time for sure. Again, thanks so much.
Bye. Bye-bye.